Are you ready for some calculus? I am. Chapter 2, Section 6, Derivatives of Inverse Functions. The bullet points seem pretty straightforward. Find the derivative of an inverse function. Differentiate an inverse trigonometric function. That's just going to be memorizing some formulas. So, the derivative of an inverse. The next two theorems discuss the derivative of an inverse function. The reasonableness of Theorem 216 below follows from the reflective property of inverse functions. As shown in figure 229, let's slide this over and check out the figure. So we've got a couple of graphs here. In darker ink is y equals f of x. One of the points on that graph is a comma b. We've got our y equals x line. Remember, if we reflect over that, that is our inverse function. So if we reflect the darker line over that line, we get this lighter gray function that is f inverse of x. And make note of the point. This point a comma b on f of x has now been reflected to b comma a on the other function, on the inverse function. Inverse functions have reflected points. So here in Theorem 216, they're talking about continuity and differentiability of these inverse functions. The setup is let f be a function whose domain is an interval I. If f does have an inverse function, then these statements will be true. If f is continuous on the domain, then the inverse will also be continuous. Number 2, if f is differentiable on an interval containing c, and that derivative does not equal 0, then the inverse is also going to be differentiable at that point. So if function is continuous, the inverse is continuous. If the function is differentiable, the inverse will also be differentiable, except where the original one would have a 0 slope, a horizontal tangent line. And that leads us to this Theorem 2.7. And that says, let f be a function that is differentiable on interval I. If f has an inverse function g, then g is differentiable at any x value for which f prime of g of x is non-zero. Moreover, g prime of x is equal to 1 over f prime of g of x as long as f of g of x does not equal 0. Does that make absolutely perfect sense? Okay, well, let's move on. I'm just kidding. If we come back to this, the notation is pretty overwhelming, but we can sum this up pretty easily. Remember, inverse functions have reflected points. Inverse functions have reflected points. Reflected points. And at these reflected points, they have reciprocal slopes. At these points, at these reflected points, the function and the inverse have reciprocal slopes. At these points, reciprocal slopes. Now, if you remember parallel and perpendicular lines, the perpendicular line was a negative reciprocal. Here, we're not going to negate it. It's just going to be a reciprocal slope. You know, that's sort of making this a little bit easier. The derivative of our inverse is going to be the same slope as f derived, but we're going to invert it. We're going to flip it over. Inverse functions have reflected points, and at these reflected points, they have reciprocal slopes. Now, this one here, example 1 can be a little intimidating, but I think I've got it down to a point where I can make this pretty simple. So they give us f of x, that is 1/4 x to the third plus x minus 1. Part A, what is the value of the inverse function, f inverse, when x is equal to 3? And part B, what is the value of f inverse prime, the inverse's derivative, when x is equal to 3? Well, if we try to start solving this to turn it into an inverse, we're going to get stuck because of the cube in the first power. But let me do it this way. I'm going to sort of split my screen here. And on the left, we're going to talk about f of x. And I'm just going to write it in here now. F of x is 1/4 x cubed plus x minus 1. Over on the other side, I'll even switch to blue ink. This is going to be f inverse of x, and we do not know what that function looks like at all. And let's go back up to the setup. What is the value of the inverse when x is 3? So over here, if we had the function, we could put in a 3 and out would pop the number that they're asking us for. But we don't have the function to do that with. Let's think back over here to f of x. If 3 comma question mark is on the inverse, then that means over here there's some x value that's going to give us an output of 3. Can we figure out what that x value is going to be? Absolutely. So usually, these problems are designed to be solved. We can just try a little plugging and chugging. F of x is up here. If we do f of 0, that would be 0 plus 0 minus 1. That's not the output that we're looking for. What if we tried 2? 2 to the third is 8. 1/4 of 8 is 2. Plus 2 more would be 3. Minus 1 would be 2. No, hold on, I messed something up in there. 1/4 times 2 cubed would be 8, and then plus 2, and then minus 1. So 1/4 of 8, that would be 2, plus 2 more would be 4. 4 minus 1 is 3. So we found it. That question mark I can get rid of, and we figured out that's going to be a 2. The original function, f of x, has a 2 comma 3. So that means on our inverse, the reflected point is 3 comma 2. So we've answered part A. What is the value of the inverse when x is equal to 3? Well, that output is 2. Now in part B, they're asking us about the inverse's derivative at that same point. Well, we don't have the function here, f inverse, so we can't derive it and plug the 3 in. Let's go back over to f of x and find its derivative. F prime would be 3/4 x to the second power plus 1. Now, if we plug, let me get a little more room to write over here. I guess I didn't get rid of too much. Okay. So we can find our reflected point. I shouldn't have erased that. That was 2 comma 3. So we can use f prime and plug in this x value of 2 to get f prime of 2. That's going to be 3/4 times 2 squared. That's going to be a 4. That's going to turn into a 3 plus 1. So our slope over here is 4. If we found this slope is 4, or 4 over 1, the inverse function is going to have the reciprocal 1/4. We have a reflected point, 2 comma 3, and 3 comma 2 is the reflected point. Over here, our slope was 4 over 1, so we invert that for 1/4 on our other point, our reflected point on the inverse. What's this? In example 1, note that the point 2, 3, the slope of the graph is 4. At the point 3, 2, 4, the slope of inverse is 1/4. The reciprocal relationship is sometimes written as this. So dy dx equals 1 over dx dy. I guess they're just, inverting that Leibniz notation. Okay, that was a fun. Ooh, what do we got here? Yeah, here, this one, our slope was, this was 2 comma 3, 2 comma 3, and the slope was a nice steep 4. Over here, the point was 3 comma 2, and our slope was 1/4. There we go. All right, this is a great example to really show this. Let me move this over here. F of x is x squared for all positive x's. And f inverse, of course, the inverse of squaring is square rooting. Show that the slopes of the graphs of f and its inverse are reciprocals at each of the following points. So again, I'm going to sort of split my screen here. And on the left side, we're going to do, let me get rid of that, f of x equals x squared. That is our function. And on the other side, we're going to do f inverse of x. That is x to the half power, or the root of x. Well, all right, let's derive each of them. Over here, f prime, simple power rule, 2x to the first. On the other side, not so simple power rule, f inverse of x, and this is going to be f inverse prime. I should have a prime up there. So we're going to bring down the half, 1 half x to the negative half. So that's going to be 1 half, and we're going to have x to the negative half. So let's put it back down here and put it back under a radical. So we have f and its inverse, we have f prime and f inverse prime. So now let's analyze the points they gave us. So the first one here is 2, 4. So that's going to be for the squaring function. If we put 2 into x squared and we square it, we get 4. So our derivative here is going to be f prime of 2. That's going to be 2 times 2, and last I checked, that's equal to 4. Now let's hop over to the other function, the inverse function, where the reflected point is 4, 2. In the square root function, you put in a 4. The square root of 4 is 2. So now here in this f inverse prime, we're going to plug in the 4 value. So that's going to be 1 over 2 times the root of 4. Well, that root of 4 is a 2, so that denominator is just 2 times 2, or 4, 1/4. So I'll say it again. We have our reflected points, and at those reflected points, we have reciprocal slopes, 4 and 1/4. We've got another point to do that too, though. We've got 3, 9, and 9, 3, just to have a little more fun. So back over to x squared. The point 3, 9 is on this graph. If we square 3, we get 9. So f prime of 3 is going to be 2 times 3. And that's going to equal 6. So we could say, okay, if this has a slope of 6, what's our reciprocal slope over here going to be? 1 over 6. But let's just check it to have fun anyway. Our reflected point is going to be 9, 3. We root the 9, we get the 3. So f inverse prime of x is going to be 1 over 2 times that root of 9. The root of 9 is 3. You multiply it by the 2, and you get the 1/6 that we were expecting. Isn't calculus fun? Here's a graph so we can see what's going on. The darker black one is the x squared graph, and then this one opening up sideways, that is our root of x. So let's see, the one we just did, we were way up here, that was a steep positive 6 slope. Over here it is 1/6. And the first one we did was 4 on the squaring function in red. That slope is positive 4. Over here on the inverse function, it was 1/4. All right. Example 3. Oh, look at that directions. Find the derivative of the inverse tan function. This is new to this textbook, and I kind of like this example. It's pretty straightforward. Derivative of inverse tan function. So we are going to let f of x equal tan x. And of course, that's going to have an inverse, f inverse of x. And just for keeping the notation a little cleaner, let's rename this one g. And what's the inverse of tan? Well, that's arctan, the good old arctan function. All right, when we are going to restrict, remember to have an inverse, we're going to have to restrict tan just from negative to positive half pi. So if we don't restrict it, we don't have an inverse, so that's sort of implied that we're going to have that restricted interval. All right, so we've got f. Let's find f prime. What is the derivative of tangent? Remember my little mnemonic trick to remember that. Secant, secant, tan. So the derivative of tan is going to be secant squared of x. Now if we think back to pre-calc, Pythagorean identities, sine squared plus cos squared equals 1, there is one for secant squared. That is the same as tan squared minus 1. Minus 1. Oh, that's going to come into play in just a little bit. Okay, now for the confusing notation from that theorem box. G prime of x Remember that g is our inverse here. G is our inverse. So this is going to be the inverse of that, and that's what they're asking us to find in this example. That is going to be equal to 1 over f prime of g of x. And I guess I need another parenthesis on there. So that's the same as 1 over f prime of, well, g of x we know. This g of x is arctan. So I'm just going to put f prime of arctan x in there. Okay, now I'm going to have to erase something. I guess I can get rid of this. I don't want to get rid of that yet. Move this over. Okay. Now we got here f prime of arctan. So we're going to take f prime function and replace all the x's with arctans. Well, here's f prime. It was secant squared, but we did rewrite it as tan squared minus 1. So I think I'm going to have to erase some stuff up here so I have enough room. So our g prime of x, I'm right here, is equal to 1 over, we're going to take f prime and replaces the x's with arctans. So here it is tan squared of x. Let's write that as tan squared of x, and we've still got this minus 1. Let's get that in there right now so we don't forget it. And we are going to replace the x's with these arctans. So in here, well, I'm going to rewrite it as tan inverse like this because I don't have a lot of room. Remember, this arctan and the tan inverse are the same thing. Now let's see how this simplifies. Oop, and I should have, that's the tan inverse of x. I need it, that is just so ugly. I'm going to rewrite it here. The tan, I'm going to put it back as arctan because I'm going to have some more room here. The arctan of x, and that is squared minus 1. Think back to pre-calc. What are tan and arctan going to do to each other right here? Well, they're going to cancel each other out. So the tan and the arctan are gone, and that just leaves this x. So what are we left with? 1 over x squared minus 1. There's our final, oops, excuse me, that's a plus 1. That Pythagorean was tan squared plus 1. Okay, little minor mistake there, but easy to fix. Just change that to a plus. 1 over x squared plus 1 is the derivative of arctan. And that leads us to, oops, get back here. The derivative of inverse tan functions. Ooh, and hold on, let me back up. I forgot about this stuff here. This is an example from the last section. Remember, we had y equals arc sine x. We took the sine of both sides. We derived implicitly. We got the dy dx by itself. We used a Pythagorean identity to replace that denominator cos y with root of 1 minus sine squared. And then we took out that 1 minus sine squared. We could replace the sine with x, so that sine squared became an x squared. So we found this in the last section when we were finding an implicit differentiation. And that is also on our formula sheet for the derivative of arc sine x. So the example we just did in that previous one from the last section is getting us into these derivative of the inverse trigonometric functions. Back in section 2.4, we saw the derivative of the transcendental natural log x is the algebraic 1 over x. You'll now see that the derivatives of the inverse trig functions are also algebraic. They're not going to be transcendentals themselves. The next theorem lists the derivatives of the 6 inverse trig functions. Note that, they're paired up. One is just the negative of the other. So when we're looking at these, if we go straight across, they are just the negations. Here's the derivative of arc sine u. If we put a negative in the numerator, that's the derivative of arc cos. Here's the derivative of arc tan. If we put a negative in the numerator, that's the derivative of arc cotan. So the functions and their cos are just negatives of each other. So we're going to really memorize the ones here on the left, because if we memorize the ones on the left, we can just negate the numerators to get the ones on the right. Before the test, we will have a quiz on these formulas. So let me zoom in here. So we've got these three to memorize, and there are some little nuances and little tricks to them. We're going to derive arc sine, arctan, and arcsecant. Remember, this is for the composites, so this u is going to be something more complicated than x. It might be x squared or 3x cubed. But let's look at some of the similarities and differences. Right off the bat, I noticed that two of them have radicals downstairs. The one that doesn't is arctan. Arctan has no radical in the denominator. So if you see a radical downstairs, it's going to be arc sine or arcsecant. And let's look at what's going on under the radical. In arc sine, it's 1 minus some function. Under arcsecant, it's reversed. The function comes first minus a 1. And then also the dead giveaway for arcsecant is we've got this piece outside the radical. You know, whatever this numerator u is, it's also under the radical u squared. It's going to be out here in some absolute value bars. So that's going to take us for arcsecant. That's, again, the sort of the dead giveaway for that one. Okay, so the main part of these is you figure out what your u is, and then you take the derivative of u. That u prime goes up here. Down here, arcsecant, or excuse me, arc sine of u, we're going to put whatever that u is here and square it, and that goes underneath the radical subtracted from 1. For arctan of u, you know, whatever that u is going to go right here. You're going to square it, and u, whatever it is, you derive it and put it on top. Down here also, arcsecant u, you know, you're just going to have that u value. That's going to go in two spots, here inside the bars, under the radical, and we're going to square it. Derivative of u goes right on top. So here, differentiation of inverse trig functions is sometimes tested on the AP exam. The inverse sine and inverse tangent functions are the most likely topics. So if you are taking the AP test, make sure to have down cold arc sine and arctan. So let's try these out. All right. So here, first one, we are going to derive arc sine of 2x. So if I put a set of parentheses around that, Ru is what's in the parenthesis, 2x. Ru prime, the derivative of 2x, is 2. So now we're just going to put these in the formula. Since the formula is new to us, I'm going to copy it here. That's going to be u prime over radical 1 minus u squared. So that u prime 2, we're just going to put that in the numerator. And then we're going to have a radical. And under that radical is 1 minus. Now be careful here. That's some u squared, and we're going to put the 2x in there. Now, if you leave it like this in your homework or on a test, I'm going to knock off a point or maybe a half a point, because we should simplify that. It's just good manners. So our numerator 2 over radical 1 minus 2x times 2x is 4x squared. And there's our derivative of arc sine 2x. Find your u, find your u prime, plug and chug in a formula. Up next, B. Arctan of 3x. So our u value is 3x. Derivative u prime is going to be a 3. The arctan formula, u prime over 1 plus u squared. So the u prime in the numerator is just a 3. Down in the denominator, 1 plus our u, and that is a 3x, and that's quantity squared. Again, I'm going to want to see that simplified. So let me move back up here. Oops. So the numerator is just going to stay a 3. Down in the denominator, 1 plus 3x quantity squared is 9x squared. And there's our derivative of arctan 3x. Next up, letter C. Arc sine root x. So our u value is going to be the root of x, or I'm going to write that as x to the half. And if we derive that u prime, we'd bring the half down front, 1/2, and then it would be x to the negative half. So that's going to go back down in the denominator as x to the positive half. Okay, arc sine, we've seen this one already. That is u prime over radical 1 minus u squared. 1 minus u squared. Okay, let's start putting some stuff in. I'm going to sort of color code this. Our numerator u prime, that's the 1 over 2 x to the half. And then our denominator, let me switch to blue ink, is radical 1 minus u squared. And in for our u is the x to the half power. Now let's see if we can make this look a little prettier. You know, math should not just be correct, it should be beautiful. And this, while it's not ugly, whoa, we can make this look a little better. There we go. So, now I'm going to just do a little scratch work down here. If I had a over b, and that's all over c, we can sort of slide this fraction off the top. So that would be a over b times, well, when this fraction slid off the top, there's a placeholder 1 there, 1 over denominator c. So then we can multiply straight across and have a over b times c. And if that's confusing with numbers in it, or letters, let's do it this way. What if I had 1/5 all over 7? Well, I could slide the 1/5 off. That would be 1/5 times, when the 1/5 slid off, there's a 1 holding that numerator's place, 1 over 7. And we could write that as 1/35. So we're going to do a similar operation here. This red fraction on top is sort of going to slide down here, and the numerator 1 is going to stay with the placeholder numerator 1. So our numerator is just going to be a 1. And then this 2x to the half is going to appear here multiplied by this radical. So that's going to be a 2 x to the half, and then we still have our denominator, this radical, 1 minus, and this was x to the half quantity squared, or if you want to think about that as a root of x quantity squared, well then that would just be x. Now if you left your answer like that, I would be pleased with it. It's no fractions within fractions, so it looks pretty good. But let me even do this. If it wouldn't match the multiple choice on the AP test, let's put this x to the half back as a radical. So that's 2 root of x times another radical, 1 minus x, and that's underneath that radical. Can we do anything with that? Well, yeah, since it's a square root times another square root, you know, we can distribute that. So this is going to be 1 over. The 2 is going to stay outside. But when this other x jumps under here, it's going to be under one big radical. Now remember, radicals are grouping symbols. So this 1 minus x is a group. And then when we put it all under one big radical, that other x is just going to appear out here. So you could leave it like that. Or if you want to distribute the x under the radical, that would also be acceptable. So that would be 1 over 2, and then radical, distribute, that would be an x minus an x squared. X minus x squared. And there we go, a little more good-looking answer for our derivative of arc sine of root x. Oops. Letter D, last one. Arc secant. We have not done one of these yet, and these are always interesting when you have an e going on because e is its own derivative. So e's lead to some interesting happenings with these inverse trigs. So here our u value is e to the 2x. We need to derive that with the chain rule. The e to the 2x will derive to itself, and we will chain the inner function 2x derives to a 2. So there we go. Now this function, or this formula we have not used yet, that is u prime. Downstairs we have an absolute of u, and then radical u squared minus 1. U squared minus 1. Okay, let's do some plugging and some chugging. U prime in the top, that's going to be 2e to the 2x, 2e to the 2x. Out front of our radical down here, we have an absolute value of u, so that's just the e to the 2x before we derived it. Now underneath the radical is a u squared, so here is a u squared minus 1, and the u value we're plugging in is e to the 2x. If you leave it something like that on a test or a homework, it is not simplified. We should simplify our answers. And let's see here. Not much we're going to do with the numerator. Oops, what did I lose there? I lost that exponent. So the numerator, 2e to the 2x is going to stay. 2e to the 2x. Now, are these bars necessary? E to the 2x, it's a positive e to the 2x. Exponentials are by default positive. Remember, e to the x, get over there. Any base to the x power is going to be an exponential, goes through 0, 1. It is always above the x-axis unless shifted down. So in this case, the bars are not necessary. So that's just going to be an e to the 2x. And we're going to multiply that by, well, underneath the radical, it's e to the 2x quantity squared, or e to the 2x times itself. Little scratch work here, e to the 2x times itself. What do we do with the exponents when we multiply like bases? We add them. So that's going to be an e to the 4x minus 1. So there's a little nicer answer. Did you notice there's one more thing we can simplify? In the numerator, and one of the terms in the denominator can cancel. This is a 2 times e to the x, so we've got down here this e to the 2x times our radical. So we can simplify or eliminate e to the 2x in the numerator, e to the 2x in the denominator. So our better looking answer here is 2 over root e to the 4x minus 1. And there's our derivative. Okay, is this one more example? Yes, this is our grand finale. This is a biggie. We're going to bring back some stuff from deriving chain rule and factoring out least powers. So here they want us to derive this, y equals. So we've got an arc sine. We've got a new formula to deal with that. And then here's an old friend, product rule, first term. And we've got a second term, so that's going to be definitely a product rule and something we can simplify. All right. I'm going to, excuse me for my notation, I think I'll put it up here, y prime equals, but I'm going to start my derivative down here. And thankfully, this is just arc sine x. It's not arc sine of some function u. So this is going to derive nice. Let me just click back to that slide. Oops. So the derivative of arc sine x, the u prime is just going to be a 1. So that's 1 over radical 1 minus x squared. Go back here. So that's going to be 1 over radical 1 minus x squared. Oop, that's a terrible 2. That's even worse. This, if I can't, 1 minus radical 1 minus x squared. I guess I can't write too small there, but now I can do this. So there's the derivative of arc sine. I'm just having a bad time with this. Radical 1 minus x squared. Plus, now we got to do a product rule. So the derivative of x is 1, and the derivative of this, let's do a little scratch work, that's going to be that quantity to the half power. So we're going to bring the half down front, have the 1 minus x squared still in there to 1 power lower, minus half power. And then we got a chain rule, that inner function, that's going to be times a negative 2x. So to simplify this, the negative 2x times a half is going to be negative x, and then we're going to have our quantity to the negative half power. Now we're going to leave that as the negative a half power until the very end. So this is negative half power. So we have x and its derivative 1. We have that radical and its derivative right there. So let's do the product rule. And actually, so I have a little more room. I'm going to move this just down here. Whoa, down here a little bit. Okay, so we're going to have the first thing, x, times the derivative of the second thing. So let me even back that up. This x times this negative x is going to make that a negative x squared times the quantity to the negative half power. Product rule goes on to say plus the second thing times the derivative of the first. Well, that's the second thing is our radical, 1 minus x squared, times the derivative of the first was just 1. Okay, here is our raw derivative, and it's just atrocious. It's got negative exponents. It's still got radicals and different stuff. So let's get all the radicals out of there and turn those all into rational exponents and see what we can do with this. So this first term here in red, well, this down in the denominator is going to be a half power, and let's bring it up. So that's going to now be a negative half power. 1 minus x squared to the negative half. The middle term, we're going to have a minus. We've got our x squared times 1 minus x squared to the negative half. And then our last term plus, this is just a square root. So that's going to be 1 minus x squared to the positive half power. And of course now we are going to factor out the lowest power. All of our bases are the same, so we can factor out the least of them. So I'm going to use a little blue here. They're going to put a big old set of blue brackets around that. And we are going to factor out the lowest power. Our base is 1 minus x squared. Our lowest power is negative half. So that's what we're factoring out. Now let me put the blue brackets back in and see what's left inside. Well, this is our base to the same exponent that we factored out. So we have factored that out in its entirety. That's going to be replaced with a 1. Minus. The next term is right here underlined with this blue. We have factored this base out to the exact same exponent, so that was pulled out. We can replace that with a 1, but there's still an x squared there. So we've got an x squared in here. And then plus, now the last term, our base is 1 minus x squared. But we factored out the least exponent, so we've got a new exponent here. So we could figure this out by going 1/2 minus this negative a half. 1/2 minus a negative a half is going to be a half plus a half, or 1. Okay. One more thing to simplify this. Within the blue brackets, we're going to drop the parenthesis because it's just a first power, and this is a plus. So if we distribute a 1, the parenthesis will just disappear, and we can combine like terms within the blue brackets. I'll stick with blue brackets. So if we distribute a positive 1, this is going to be a 1 plus a 1. Well, that's just going to be a 2. And we're going to have a negative x squared and another negative x squared. Well, that's minus 2 of those x squareds. And then let's get rid of our negative exponent. This negative exponent here, we'll just move it down into the denominator, and we can make it into a positive exponent. 1 minus x squared to the half power. Now, if you stopped right there, I'd be okay with that. It is a good-looking answer, but it's going to get even more beautiful. More algebra. What can we factor out of the numerator here? A 2. So if we pull out a 2, we get a 1 minus x squared. Our denominator, 1 minus x squared to the half power. It looks like we are now dividing the same base. Up top, this implied exponent would be first power. So when we simplify this, we're going to have a 2, and we know we're going to have a 1 minus x squared base, but what's our new exponent going to be? Subtract. 1 minus 1/2 is a half. And then I guess it looks nice. Let's put it back under a radical. That quantity to the half power, let's just put that back under a root. 1 minus x squared. So I've done a lot of erasing, but if you look in your notes back from our raw derivative to what we've got here as our final answer, that is quite a simplification. So again, we derived the arc sine of x plus x times the root of quantity 1 minus x squared, and that derivative turned into that little beautiful answer right there. Very nice. Okay, I think we just have a wrap-up slide. Oh, a little bit here. Well, you can read that on your own. I won't make this video any longer than it needs to be. But here are a bunch of functions that we have learned to derive. Basic differentiation rules for elementary functions. So this is just all the stuff we've been doing up until now. The constant multiple rule, derivative of a sum or difference. There's the good old product rule, quotient rule. Derivative of a constant is 0. There's just our general power rule, bringing down the exponent. Derivative of x is 1. Natural log u prime over u. Our non-base e exponentials, log logs, exponentials base e. Our derivative of sine, cos, tan, all 6 trig functions, and now we have all 6 trig inverses. So 24 derivatives to get you through the tough times. I think that's the end of the slideshow. Next time I see you, we'll do some odd problems.